inverse trig depth you guys go into in honors pre-calc, and they showed me that you do see the graphs, but it's still kind of a weird thing, so we're spending some time redeveloping the graphs. And the big idea with all of our inverse trig graphs is that because our trigonometric functions are periodic, meaning they keep repeating their values, they are not one-to-one. There are multiple spots along your x-axis that will give you the same function value, which is an issue when we want an inverse function because we need the function to be one-to-one. And so our trick is to restrict the domains of the given trig function and then define the inverse trig function only on that domain. And so we kind of see the resulting graphs for the sine and the cosine. And again, as we work through these, understanding that the inverse sine or the arcsine, because it is the inverse of the sine function, we ask ourselves, what does the sine function do? Well, it takes an angle and then gives you some sort of ratio or some sort of y height. The inverse sine then does the opposite. It's going to take a sine value, like -1, and tell you the angle that produces that sine value, which is another way of sort of illustrating why it's important to restrict the domain. Because if I tell you sine of -1, there are an infinite number of locations, an infinite number of angles that can give you a sine of -1. Just keep going around the unit circle. And so the restriction to the domain means, oh no, for the inverse sine, if I give it a -1, the only answer is -pi/2, because we are restricting it to live in this space. And we did something similar with the cosine. And then the question was, okay, now that we have these graphs, clearly these things look continuous, and they seem like they should be differentiable since they are the inverses of differentiable functions. So what are those derivatives? And I believe all we did on Friday was the sine. Let's take a quick look at that again.
I think we did sine and cosine.
And in deriving all of these derivatives, we're going to follow sort of a similar pattern where we're going to start with our, there we go. We're going to start with our inverse trig function, but then use the definition of the inverse trig function that if y is equal to the inverse sine of x, well, that can only be true if x is equal to the sine of y. And then we try to find the derivative using this equation. And in each case, we're going to kind of run into the same situation where trying to find the derivative is going to sort of throw us into the situation that involves y. And so we're going to have to play this game to try to redefine a certain part of this derivative. And so what we saw with the sine is that we ended up with dy dx was 1 over the cosine of y. You don't need to write this down, it's kind of just review. But it's not terribly useful to have a derivative that involves another function, y in this case. And so we were able to, through our trig identities, come up with cosine of y is actually the square root of 1 minus x squared. And then this is our definition of the derivative of the inverse sine. And then we saw a quick example of that. The derivative of the inverse cosine will follow in a similar manner. What about dx of inverse cosine. Well, if we let y equal the inverse cosine of x, this will be true if and only if x in turn is equal to the cosine of y. The cosine of some angle is x, well, then the inverse cosine of that x gives you back that angle. I'm going to do this slightly different than the inverse sine. On the inverse sine, we sort of played around with the dx dy idea. So you'll notice that the variables were different, that we differentiated with respect to y. I don't want to do that here. Here, we're just going to differentiate with respect to x and see what happens. So we're going to go differentiate with respect to x on both sides. What's the derivative of x with respect to x? 1. What's the derivative of cosine? Negative sine of whatever it is. In this case, y. But whatever it is happens to be a function. Y is the inverse cosine. And so when we differentiate, this is a composite function, this inner function, we need to use the chain rule to break out dy dx. This is what we're after. And what about dx of this is the same thing as d dx of cosine of x. We want the derivative of y with respect to x, sorry, inverse. So rearranging this, we get that dy dx is equal to 1 over the opposite of the sine of y. But again, it's not that useful to us to have a derivative of y that involves y. We want the derivative to be a function of x. And so we're going to look again to see, is there a way we can redefine the sine of y in a way that is more useful to us? Because quite literally, if we wanted to, we could substitute back in for y and say, okay, well, you want a derivative that involves x's, put the inverse cosine of x back in there. Then it's like, what is the opposite of the sine of the inverse cosine? That just, let's make it look nicer. So the identity that we're going to look at, basically for every single one of these, really the only trig identity that you really need to memorize in my mind is the cosine squared of something plus the sine squared of that same thing is equal to 1. And really, you already knew this from geometry, because why does this work? Triangle, our favorite dead Greek mathematician Pythagoras. We recognize that the cosine is the x and the sine is the y on our unit circle. Those are the legs of a right triangle whose hypotenuse is 1. This is Pythagoras. Always good to keep that in mind. And so we're looking for a definition of sine. So the sine squared of y is equal to 1 minus the cosine squared of y. We started this process out by saying that the cosine of y is x. That was the nature of that inverse relationship. We can rewrite this as the sine squared of y is equal to 1 minus x squared. We don't particularly care about what the sine squared is. We just want the sine of y. Taking the square root on both sides, we get that the sine of y is equal to the square root of 1 minus x squared. Well, that is helpful. Now we can take this back into our derivative. So the derivative of y with respect to x is equal to 1 over the opposite of the sine of y, the square root of 1 minus x squared. Or more generally, to account for the potential that x itself is a function. Put down here. We'll do, sure, 5.7. I'm going to guess it's 5.7.3. Maybe I should check that. That doesn't really matter, but 5.7.4. Good thing I checked. Here. If you can't see that, can we? There we go. It's pretty now. This dot canvas, not long for this world, I don't think. If u is a differentiable function of x, then the derivative with respect to x of our inverse cosine of u is equal to -1 of the square root of 1 minus u squared times the derivative with respect to x of u. Oh, happy day. Let's do a quick example of that, and then move on to the tangent. Example 4. Is y is equal to the inverse cosine of e to the 2x. Ooh, that's fun. We are tasked with finding dy dx. So dy dx will be the -1 over the square root of 1 minus u squared, u here being e to the 2x squared, times the derivative of x of e to the 2x. So this turns into -1 over the square root of 1 minus e to the 2x squared. Looks a lot like e to the 4x. The derivative of e to the 2x, which is kind of nice, drawn some previous chapter 5 knowledge. Well, the derivative of e is just itself, e to the 2x. But then we do have to account for any sort of chain rule with its exponent. The derivative of 2x is 2. And so final answer, dy dx is equal to -2 e to the 2x diviso a 1 minus e to the 4x. Cool. Cool. So just kind of another tool in our tool bag to be able to differentiate a new type of function. Yeah. Okay, so now we are going to actually flip back into the packet, and we're going to flip actually past the third page that has the secant and cosecant and go to the fourth page that has the tangent and the cotangent. And we're going to look to see if we can restrict the domains and come up with some sort of reasonable graph for these two things, and then look to see if we can define derivatives. So, there's the tangent and the cotangent. Again, what we are trying to do is find a what is the word I'm looking for? An interval, interval, Tuesday, give me a break, where our tangent is monotonic, so either always increasing or always decreasing. Well, looking at that curve, when it's defined, it is always increasing. Okay? Tangent is always increasing. It does have these sort of built-in asymptotes every pi when our tangent blows up. Okay, so when our cosine goes to 0, the cosine being the denominator of our tangent ratio, it goes haywire. And so we have these kind of natural breaks in our tangent, and that's where we're going to take our restriction. That if we want a monotonic curve, seems like if we just restrict the tangent domain between -pi/2 and pi/2, that would be a pretty good call. Did we go like full fuzzy on the other ones? I don't remember. What did we do? What did we do? No, we just outlined. Cool. So one of these pieces is going to be the thing that we invert. The thing that we invert. Cool. So our domain restriction on the tangent is going to go from, I guess it needs to be parentheses here, -pi/2 to +pi/2. The range appears to have no restriction. Seems like that would just go off towards positive infinity, down towards negative infinity. So we'll say that the range is negative infinity to positive infinity. So we know that our inverse to this then is going to have flip-flopped domain and range. That's specifically the inverse tangent let's call this just tangent 1, or the arctan, helps sort of avoid the confusion sometimes implicit when we use a -1 here. It's going to have domain and range that swap. The domain of our inverse tangent is actually going to be all real numbers. That's the range of our tangent. And the range of our inverse tangent is going to be restricted between negative pi over 2 and positive pi over 2. Kind of sort of picturing this a little bit. So no restriction on our domain. And especially if we try to sort of visualize what a reflection of this curve over y equals x equal, or looks like, kind of gonna like almost rotate it. But let's see what that looks like. Do a little XY table. How did I do 3? Yeah. And again, the mental processing that we're doing is the tangent takes an angle and gives you the tangent ratio. So the inverse tangent is going to take as inputs the tangent ratio and give you the angle that produces that ratio. Kind of the easy tangent ratios are -1, 0, and 1. Maybe starting with 1, as odd as that is. Where do we get a tangent of 1? What angle produces a tangent of 1? Pi over 4, it's a 45-degree angle. That's when the legs of that right triangle are the same. For -1, it should be a -45-degree angle, or negative pi over 4. And then for 0, where do we get a tangent of 0? Should be at 0. So now we're armed with a little more detail. I'll try to build this out. We do have this sort of awkwardness of our axes are a little bit off. So we're going to have to sort of adjust as we go. Pi over 2 is 1.57. So we're looking for 1. So 1, 2, 3, 4, 5. So each of those is about 0.3. So we're going to say that 1 is just after the third tip, maybe right around the third tip. Pi over 4, I don't know what that is. Pi divided by 4 is 0.78. So we're going to go, so 1 pi over 4, I'm going to this third tick mark on the x-axis, and then up to 1, 2, 3, just 4 here, just past the third tick mark on the y-axis. A little bit funky. 0, 0 is simple enough. And then same sort of trickiness here for -1 pi over 4. We're going to go just past the third tick mark, and then just past the third tick mark. There's -1, -5 over 4. And then I think before we try to sketch this curve, it would be useful for us to draw in the the range restriction to kind of give us the outermost boundaries. Because again, the inverse tangent is going to have no domain restriction. We're going to have a continuous curve all the way. It will, however, have these boundaries top and bottom from this range restriction of -pi/2 and pi/2. So let's go in and around 1.5, make a little dotted line that we're not going to cross. So just past 1.5, make a little restriction here. And then just past -1.5, do the same. So then our curve, a little bit, it doesn't ever actually cross over the tangent. It sort of just kisses it. So it's kind of like a kiss, kiss, and then goes off towards like that. Cool, cool, cool. The inverse cotangent proceeds in a pretty similar fashion. Their inverse cotangent also has this constantly monotonic, in this case decreasing characteristic, also truncated at regular intervals by these hot spots, these spots where our sine is 0. Because the cotangent is the cosine over the sine, and so any spot that gives us a sine of 0 is an issue for the cotangent. So that gives us a nice natural domain restriction here. And if we restrict our domain between 0 and pi, that gives us the monotonic invertible function that we're looking for. Horrendous mistakes here. Yeah. So our domain restriction here is from 0 to pi. Oh, don't know why I keep trying to do brackets. Our range is all real numbers. So then as we change gears and look at the inverse cotangent, or the arc cotangent, these are going to flop. And again, we're going to have a domain for our inverse that's actually all real numbers. And a range that is restricted between 0 and pi. Building out a small table of values. I'm thinking that those are probably going to work again, right? I don't know. It didn't work this far ahead. We should probably have, let's think about this. Yeah. -1, 0, and 1 should be easily attainable cotangent values. Let's think about where those are going to happen. So cotangent of 1, oh, we got to be tricky now because our domain, oh no, it doesn't matter. Yeah. So we get a cotangent of 1 also at pi over 4. And a cotangent of -1 also at negative pi over 4. Now we got to think, where do we get a cotangent of 0? In other words, where is the cosine equal to 0? Pi over 2. Is this going to be enough information? Nathan.
The -1 you do pi over 4 because negative pi over 4 is not oh yeah.
It's in our range, but yeah, let's think about this. It still needs to be in the domain of this. Yes. So the -1 value needs to spit out 3 pi over 4 because negative pi over 4 is not in the domain of the cotangent that we're inverting. So it's 3 pi over 4. That will make more sense. Pi over 4, 3 pi over 4, pi over 2. Okay. Let's see where this ends up. So the, yeah. Okay, so -1, again, kind of lives in this weird spot that is just past 3 tick marks. And that's going to give us a value of 3 pi over 4, which, I don't know if I know what that is. What do you get when you cross an elephant and a rhino? Hell if I know. I got dad jokes for days. 2.35. So we'll go -1 is just about here. Oh, this can be off. Oh yeah, this is awkward because our range restriction goes from 0. And next year I need to choose a more inclusive graph. The pi up here is 3.14, so call this pi. And so this -1 corresponds with 3 pi over 4, which is 2.35. So now we are truly kind of guessing. We're off the graph. Cool, I guess. At 0, we're at pi over 2, which was that 1.5-ish number. And then at 1, we are at pi over 4, which is that just about there. So it's kind of perplexed by this. Doesn't seem like it's going to work nicely. I think what we're looking at is something like I guess that kind of works. It's not the nicest thing, but there you go. Yeah, I kind of buy that that would be a reasonable reflection over y equals x. If you extend that, it maybe helps the visual. Cool. Again, the graphs are not really the focus here, but they do sort of help. It's the derivatives. We now have 15 minutes to cover. I think that should be enough. Cool. So we're gonna go back into our notebooks. Find mine. And see if we can figure out what the derivative of the inverse tangent has to be. What is the derivative of this curve? Let's see. What is dy dx if y is equal to the inverse tangent of x? Well, again, we can sort of brute force this to a point. So if indeed we're letting y equal the inverse tangent of x, this necessarily means that x must be equal to the tangent of y. And so sort of brute forcing this thing to try to get out dy dx means differentiating with respect to x. The derivative of x with respect to x is just 1. What's the derivative of tangent? Ooh, going back in the Wayback Machine. Secant squared of whatever. Well, r whatever is a y, is a function of x, which chews up the chain rule and spits out dy dx. Oh, that's what we're looking for. That's nice, kind of. So now we can come up with an intelligent statement about what dy dx must be. It's got to be 1 over the secant squared of y. Sort of brute force. But just as was the case with the sine and the cosine, this is not really a workable definition of a derivative. To define a derivative in terms of the function that it's the derivative of is sort of a non-starter. So we need to again work some magic here on secant squared y. Well, luckily, Pythagoras still holds court here, because this cosine squared y plus sine squared y equals 1 can be sort of remaneuvered in ways that are helpful to us. Okay? And so the remaneuvering we can do here is to divide both sides by the cosine. Cosine squared, rather. Cosine squared y, cosine squared y, cosine squared y. How does that help us? Well, it turns this guy into a 1, turns sine squared y over cosine squared y into a cotangent squared y. That's not right, tangent squared y. And it turns 1 over cosine squared y into a secant squared y. Oh, secant squared y, secant squared y. So now we can say that the secant squared y is equal to 1 plus the tangent squared of y. And we're like, yeah, let's go sub that in. But then we haven't really solved the problem, because now we've just substituted one expression that involves y with another expression that involves y. Huh. Oh, we know what the tangent of y is. It's x. So we can write this as secant squared y is equal to 1 plus x squared. And that is what we will use in the definition of our derivative. 1 over 1 plus x squared. All based on this Pythagorean identity. Or to put it more generally, theorem 5 point something something, 5.7.6. Yeah. If u is, that's not good English. If u is a differentiable function of x, then the derivative with respect to x of the inverse tangent of u is equal to 1 over 1 plus u squared times the derivative with respect to x of u. Cool. And then, since we're running sort of low on time, and because it might be fun for you to try to do this on your own, I'm just going to jump straight to the part where I give you the derivative of the inverse cotangent, but promise you that it looks very, very similar to this in terms of how to derive it, and maybe challenge you to do that on your own if you're so inclined. But this will be theorem 5.7. We do kind of a weird order in the book. 5.7.10. I guess it kind of makes sense, but it kind of doesn't. Is that if u is, again, English much, a differentiable function of x, then the derivative of the inverse cotangent of u going to be equal to the opposite of 1 over 1 plus u squared times the derivative of x with respect to u. These look very similar, just as arc, cosine, and sine inverse derivatives looks similar. There's a negative difference. And that, I think, is about all we're going to get to today. Again, I believe that if you followed the blueprint for the tangent, you could show this. Okay? You meaning you specifically sitting in the shares. I know that you can in a general term, but you'll be able to show that. Let's see if we can get started on 5.7. See. Do a new share for the kiddos at home. Here, we'll see. And do share. Sure. So 5.7 looks like a lot of problems, but they're all individually listed. There's no ranges there. 135. Because I didn't actually assign this last week, did I? So don't do it. Yeah. 135 is just doing inverse trig values. Like, what's the inverse tangent of 1 over the square root of 3? You can do that. 7. Yeah. 11. Sure. Yeah, a lot of these first half are just like re-waking your brain to what the inverse trig functions do. And then starting with 30, I need you to do the graphs. I see 5.7. I don't really care about that. You can skip 25 and 27, heck, and 29. I don't really foresee that the graphs of these things are going to feature heavily. You can skip 25, 27, and 29. Maybe just put them on your graphics calculator. I don't need you to sketch them. So basically 25, 27, and 29 give you an inverse sine, an inverse tangent, and an inverse cosine. But there's like phase shift and like a period change, and they want you to graph them. Just plug them into your calculator and see what they look like. I do not see that you're going to have to do that on the AP test. So don't do those. And then starting with 33 is where you're actually finding derivatives. And just do the ones that you can. If you get to a secant or a cosecant, obviously don't do it until you learn how to do that. Mr. T.
Do you remember any problems off back?
Oh, that was so long ago. 27. Did I not post 5.6? You got an extra day. Okay, I'll add that to my list. And you're saying I told you not to do 27? Okay. Cool. Well, then tomorrow we will tackle, I don't even know if we're going to spend a lot of time on the graphs of the secant and cosecant inverses. We might just go straight to the derivatives and then see if we can maybe start the trig integrals. Let's see what the Miss Rice pacing guide says we should be doing.
Mr. Smith,
What's up?
for the AP test, would we have to like memorize like every single one of the derivatives?
I'm gonna double check on that because I don't know the exact format. Because I know that it's supposed to be in person, but I don't know if everybody's in person. And last year it was totally open note. So I will get back to you. But in a normal year, yes, you would have to memorize those. So she had us finishing 5.7, which we didn't really do. Okay, so there's your trapezoidal rule. Yeah. So we're probably pushing closer towards, so here's Tuesday, Wednesday, Thursday. She has Thursday. So we're pushing probably towards this window for our test, where she's doing it on this Tuesday or hoping to. I don't think I'm comfortable giving you a test on a Tuesday when I don't see you on Monday. So we should be okay. We'll finish 5.8 Is tomorrow Wednesday already? We'll get it in. But let's tentatively say our test. If you want to pencil this into your notebooks or your little. You guys have planners still for the thing? No. Next Wednesday and Thursday will be the Chapter 5 test. We'll see what we can see. Okay, that's all I got. You guys are free to go. Have a wonderful day. I will post homework assignments and FRQs and all that during first period.
Thank you.
You're welcome. First period is
Thank
kind of
you.
like catch up. We don't have a class. Where I realize how far behind I am and everything.
Oh, Mr. Smith,
What's up, Edgar?
could you go back to that last theorem?
Go back to what?
The last theorem, the cotangent one.
Yeah.
Thank you.
You're welcome. Have a wonderful Tuesday. See you guys bright and early tomorrow. Can't hardly wait.
Cool, got it. Thank you.
All right. See you tomorrow.
Hey. Oh, also, have you taken a look at the recommendation?
I saw that the email showed up in my inbox. I'll
Okay, cool.
probably look at it today.
Okay, cool. Yeah, you have till the 30th, I think.
Cool. I will probably use just about every day until then.
Okay, cool. Thank you.
Yep. No worries.
See you.